Giovanna on observation of solar atmosphere.
Thank you very much. So good afternoon to everybody. Before I start on this topic, I actually asked about the question that somebody from the audience a couple of days ago asked about why basically in the when I show you a plot of the line intensity for methane with all the transitions, the question was why the maxima at high temperature seems to indicate a lower intensity compared to the transition at lower temperature. And the answer is actually what I think Tristan suggested, that the partition function at the denominator is so large that basically that's the reason why there is this this difference. So I know there are some bets going on about that answer, so I hope that some of the people who made some bet got the right response. Okay, so back to observations. I will start by looking at the geometry of transiting planets. You all know what transiting planets are. They can be in front of the star or behind it, and we can use this geometry conveniently to separate the light between the planet and the star. So how can we probe an exoplanet atmosphere? One of the very useful techniques that have been used is the transit spectroscopy. And basically what we're doing is to look at the stellar photons that are filtered through the atmosphere of the planet. And so we're looking, if you remember when we discussed a couple of days ago a bit of spectroscopy, effectively what we're using is the Beer-Lambert law, so basically the transmission spectroscopy sort of equations. And we're looking at a signal that typically, to get to the atmosphere of this extrasolar planet, is about 1 part in 10,000 the flux of the star. So of course this is a very tiny signal. Transit spectroscopy is quite useful to probe some properties of the atmosphere. As we will see, transit spectroscopy and eclipse spectroscopy are quite complementary to each other. So let's see what are the pros and the cons of all of these techniques. So certainly it's quite good at looking at the scattering properties of the atmosphere. If we're doing transit spectroscopy mainly in the visible part of the spectrum, you might remember that actually when there are some particles, some clouds, or some molecules in the atmosphere, these particles tend to scatter light. And so if we're looking at a transit spectrum in the visible part of the light, you can certainly get some information about the scattering properties, meaning whether there are some clouds and whether, on the contrary, there are no clouds or aerosol in the atmosphere. We can also probe a bit the scale height of the atmosphere, meaning how compact is the atmosphere of this extrasolar planet. And this because basically if the scale height is small, and so if the atmosphere is particularly compact, as you can imagine, the photons will have some problem to go through this relatively dense atmosphere. And so by seeing what is the amplitude of the signal on my spectrum, I can basically get some information about what is the mean molecular weight of the atmosphere, so how compact it is. Scale height and mean molecular weight are related because you might remember that the scale height is, let's see actually.
It's written up there. H equals c squared upon g.
Okay, yes. So here it is. Well, I wanted to write it as kT over mu g, mu meaning the mean molecular weight. So since these planets are already discovered with some other, with transit and presumably radial velocity, we know to a degree the gravity, and so if you know more or less the temperature of the atmosphere, you can get basically what is the mean molecular weight of the atmosphere. Looking at the third diagram, of course, we can also looking at the absorption properties of the atmosphere, in particular if there are some molecules that are absorbing on different wavelengths, then of course they will leave a trace, a signature in the spectrum, and of course also if there are some clouds with absorbing properties. So today I will not show you too many equations. I probably have exhausted all the equations in the first lecture. But anyway, this is just to collect the information that we've seen together a couple of days ago. You probably remember the Beer-Bourget-Lambert law. So again, I is the intensity of my radiation after the photons have gone through the atmosphere of the planet. The initial intensity is I0, and then there is an exponential decrease due to the opacity of the atmosphere. And this opacity, you might remember, depends on the cross-section of the particular molecule is absorbing, on the density of my atmosphere, and also the fraction of that density that is basically occupied by a particular gas. So the only thing that we need to add to what we have seen together a couple of days ago is the geometry. And so basically you can calculate what is a transmission spectrum for an extrasolar planet, basically working out this geometry. In particular, what we will do is to have a look at what level of the atmosphere my planet become opaque. And at that level, it means that I will sort of calculate a radius for the planet. But this radius, of course, is changing with wavelengths. And this is because, again, the optical depth is changing with wavelengths. So at the end, what we are basically calculating is an expression like this, where basically here I have the radius of the planet squared divided by the radius of the star squared. And this is basically the bulk of the planet, the one that is opaque at any wavelength. If it is a terrestrial planet, it is probably the radius of the surface of your planet. If it is a giant planet, is somewhere at between 1 bar and 10 bar, where basically the planet becomes completely opaque. And all this part here, on the contrary, is the part that is interesting if you want to do spectroscopy of the atmosphere, because it's the part that tells you which molecule should absorb or not. So just to show you some examples, these are just some spectra, model spectra. And basically what you're looking at here is a spectrum of an atmosphere that is dominated by hydrogen. Hydrogen is very light, has a mean molecular weight, H2 of about 2 atomic mass unit. And so clearly, as you can see, actually, this is the one H2 dominated without clouds, is in blue. It has a very large amplitude, and this is because, again, the atmosphere is very extended, and so the photons can really go through the atmosphere very easily. If we have some clouds, then clouds act as a sort of opaque layer. Of course, it depends on the type of clouds we are considering, and this is just some example. But typically, the higher are these clouds, if they are relatively thick, it means that they can sort of squeeze the spectrum, at least of some wavelengths. Then typically, of course, it depends on the size and distribution of particles. At longer wavelength, the atmosphere might become more transparent. Of course, this is just an example. If, on the contrary, the atmosphere is mainly made by a different molecule that is heavier, like H2O or N2 or CO2, the heavier is the atmosphere, the more compact it is. And then this is a zoom in of this part of the model. As you can see, CO2 then becomes really, really very flat as a spectrum. H2O, mean molecular weight of 18, is somewhere in between hydrogen and CO2, and so on and so forth. So what I'm trying to say here is that if you have a spectrum with a good signal to noise and resolution, possibly you might be able to constrain what is the mean molecular weight of your atmosphere. Yes, well, this was an atmospheric absorption, was a typical model. This is in ppm, so we are looking at, this is 2000 ppm, 4000 ppm. I think it was a specific example. So the point was just to show in relative how they're different rather than really in absolute. But basically, we are looking at the radius of the planet squared divided by the radius of the star squared in ppm. So I told you last time that it's very important to select the wavelength range at which you're doing your observation, and also for transit spectroscopy this is clearly true. What I'm showing you here is not, I'm afraid, an observation on extrasolar planet, but it's actually an observation at transit of Venus. I'm afraid we still don't have this kind of information for an exosolar planet. But this is actually very interesting. It was measured during the transit of Venus through multiple instruments in the X-rays and ultraviolet region of the spectrum. And as you can see, for Venus, there is quite a pattern. And so clearly this shows that potentially if in the future we can get a measurement in the X-rays for exosolar planet, maybe we can compare a similar sort of observations. We are already, in a sense, doing some observation with X-rays, although not necessarily so precise like the one that I show you for Venus. This is actually an interesting one. What we're looking at here, basically, is a planet that is on a very eccentric orbit. This planet is SG 17156b. And so in this figure here, we're looking at the planet when the planet is far from a periastrum, and so the contribution of the planet is negligible to this measurement, and so this is the contribution in the X-rays of the star. What is very, very interesting is that when the planet really gets close to periastrum, then the star starts to flare because of the presence of the planet. And so this kind of observation seems to suggest that you might be able maybe to look at the interaction between the star and the planet in X-rays. And in particular, that maybe some of these planets that are located so close as the star might actually sort of trigger some sort of flaring or activity by the star. Moving at longer wavelengths in the UV, there have been several observations done with Hubble, in particular with the STIS and COS instruments in the UV part of the spectrum. And the reason why you want to look at this part of the spectrum is that's because you really can probe the very upper part of the atmosphere. And as Ruth was explaining about a few days ago when she was talking about mass loss from these planets, these wavelengths are really very interesting to look at this ionized part of the atmosphere and give us some insights about this potential process of escape. So the observation I'm showing you here were done by Linsky and collaborators, and they look at several ions in the upper part of the atmosphere, OSD 209-458b. And so this measurement, coupled with also other measurements that were done, for instance, by Vidal-Najar in the Lyman alpha part of the spectrum, and other teams for other planets, seems to suggest that many of these hot Jupiters that are located very, very close to the star are losing their atmosphere in a hydrodynamic sort of way. And potentially that's why we're seeing this very strong absorption in this line, is because basically we're seeing the radius of the planet seems to be very inflated in this wavelength, again suggesting that there is a dramatic mass loss of the atmosphere in the upper part. I'm moving towards longer wavelengths, and now I am in the visible. I'm sorry that I cannot be really complete in all the observations, so I'm just showing you some snapshots that are interesting. So apologize that maybe I'm not able to cite all the observations. It's actually a good thing. At the beginning of this field, we were able to cite everything, and now the fact that we are no longer doing this is because the number of observations really is increasing, so I think this is actually a plus. Anyway, this is the, on the left, you're looking at the very first observation of an exoplanetary atmosphere done by David Charbonneau and collaborator of this hot Jupiter HD 209-458b, which is extremely famous. And so what we're looking at here is an atomic absorption in the visible by the sodium in the sodium line. And so you see that this observation, depending how large is the beam, is slightly different, the solution, but in any case, it's confirmed both with a larger beam and a narrow beam. Basically, there is a very strong absorption in the sodium doublet in the visible part of the spectrum. So this observation triggered other observations, similar observation, again for looking for sodium or other alkali metals that they all absorb in the visible part of the spectrum. This is, for instance, another one that was done for the first time from the ground by Redfield and collaborators on a different planet, SG1897333b. And I'm pleased to say that now actually the number detection of sodium lines and even potassium line is really increasing. And now for many planets, these observations are available either from space or from the ground. So clearly, this is a measurement that has been really well done by many teams. Moving to the infrared part of the spectrum, actually the combination. Okay, yes, so let's see. Is the difference in the flux, it's about 3 × 10⁻⁴, more or less. So we're talking about 3 × 10⁻⁴.
Well, the size of the planet is 10⁻², or?
Well, the size of the planet is typically about 1%, more or less. So, of course, it depends on the planet, but just to give you an order of magnitude. And so, typically, when you go to the atmosphere, you're talking about 2 order of magnitude smaller in terms of precision. Sorry?
It's just h over the
It's, yes, it's about the scale height or the number of scale height that you're probably in the atmosphere. There's this thin annulus that is representing the atmosphere. Well, certainly, well, it's reasonable if we knew what is the standard amount of sodium that we should have in the atmosphere of the planet. Back then, discussion in that particular paper and in our paper was maybe usually what you do is to look at what kind of abundance this might suggest. And then isn't this abundance well larger compared to the solar abundance or not? And if not, why we're seeing so little? Are there clouds or maybe there is another effect? For that particular observation, there was an interesting discussion whether the quantity expected should have been actually larger and whether then this was a suggestion maybe of some clouds that were masking some of the signal. Certainly what is certainly true is that we're seeing slightly different signal in different planets. Some measurements are better than others, so some measurements are easier to interpret when it comes to looking at the abundances. But I don't think we really have a clear view of what should be the standard amount of sodium or potassium in this atmosphere. We see some variability. What is causing this variability is not really yet understood, whether it's due to a contamination maybe.
Is that between planets or within the same planet?
Between planets. No, actually there are many more. Again, I haven't really cited all the observations, but now from the ground and from space there are new measurements. I just cited the very first one, but then there are many more.
The reason we can get this accuracy from the ground is because it's in a narrow filter.
It's a very narrow band, as you can probably see from, I guess I had, yes, from the model is extremely narrow. And so from space, either you have an instrument like Hubble and Hubble and STIS combined together, so a very good spectrograph, an extremely good space telescope, or is really difficult if you just have an instrument with lower resolution. It's very hard to get. You might get a little bump, but then of course you don't know exactly how to interpret that.
And in the ground, how do you do that? You take a spectrum inside and outside?
Yes, and at these wavelengths, the ground actually is quite benign, the atmosphere, and so you can usually get a relatively good measurement. Of course, it's more noisy, but that's normal. Yes. The first one from the ground is the one of Redfield, and then there is a long list from the ground. And I apologize that I can't remember all the list, but this kind of observation are becoming more and more done routinely, I should say. Okay, so moving in the infrared part of the spectrum, Spitzer, of course, is also providing an enormous amount of information, but if we're looking at spectroscopy, it's mainly NICMOS and the newcomer WSC3 that is providing a really new, very good measurement. And as you can see here, we start to have many spectra being done, especially with the newcomer on Hubble, by many teams. So this is certainly something that I'm personally very pleased of, because it means that we have new data on many new planets. And many of these data, I mean, in some cases, some data are not yet conclusive. In some other cases, on the contrary, are already providing a good insight of these atmospheres. What we seem to see out of the data coming in particular out of the newcomer on Hubble is that the two dominant sort of species that people seem to infer in this atmosphere are water vapor, in part because water vapor has a very strong signature, and even if the signal is relatively noisy, still usually something that you can, as a molecule, probe more easily than others. So if there is a bit of water vapor, then usually you're able to see it. And then some of the spectra seems to show some behavior compatible with other races or clouds, because it seems to be more flatter. In very, very few cases in transit spectroscopy, we are able to combine multiple instruments and multiple wavelengths, and with data from multiple teams. And this is one of the few planets for which this has been done, because it has been observed really over and over through years, HD 19733b. So as you can see here, the data are not always in agreement for several reasons. Actually, I have a long list of reasons why sometimes data do not agree later on, and so I don't want necessarily to spoil everything. But this is just to say that the fact that they are observed with different instruments is certainly, and in particular at different time, is certainly a concern, because most of these instruments from space or from the ground are not calibrated at the level of 10 to the minus 4, which is what we are asking them when we try to combine on a same graph all these observations. And so some of these data are taken simultaneously just by one instrument, and at that point getting to the 10 to the minus 4, I don't want to say is easy, but it's certainly less challenging. If you try to combine multiple measurements that are taken at different time, then it means you're asking your instrument to have an absolute requirement of 10 to the minus 4, and that is really, really challenging. None of the instruments today can promise you this. So of course we are committing a bit of an error when we're trying to pull everything together. So this is just my caveat. But again, putting everything together, even with disagreement about how to reduce the data, which is certainly there, but I think that the picture, at least for some of these planets, is that many of these seems to show some hazes or clouds. Certainly sodium or potassium or atomic lines that seems to be present. Water vapor also is another molecule that seems to appear. Yes?
So the differences in some of the features on the spectrum, is that real? Or is that with the data? So for example, the red points are significant. Oh, is that with the gap that you're referencing?
So here we have multiple observations, and the multiple observation by multiple team are sort of listed here. On top of that, there are 3 different models, and the models are, the difference in the model are due to different type of clouds. So for instance, one cloud model is doing this, the other cloud model is doing that. It's very colorful just because of that, yes.
Okay, so the colored lines are the models and the points are the
Yes,
okay.
yes. So you see, sometimes it really fits in data is not obvious because, again, in some wavelengths there is a bit of discrepancy among the different observations. So, but this is just to say that the overall suggestion is that hazes, sodium, water vapor, CO, possibly methane, are a typical sort of molecular atomic species that are present in this or over the planet that have been analyzed.
Well, you want to convince that all of these molecules have to flow
take all the water, show different molecules, taking out one molecule, what it makes out of the physics.
Yeah, well, yes, well,
For me, it's difficult to estimate what is the contribution of each of the molecules.
you're absolutely right. So I don't have the model of this particular planet with all these points. This is just taken out of the publication like it is. But I can tell you that in the infrared part of the spectrum, the biggest contribution is due to water vapor. This signature is just water vapor. So alone water vapor can potentially explain many of the modulation in the infrared. Then whether you need to put more water vapor or less water vapor, then we can debate, we can discuss. But the main signature is due to water vapor. CO is invisible. The reason why it's invisible, it has a signature that is very weak. And so it was detected from the ground. And in fact, I want to show you the detection from the ground of CO. So we know that must be there. But somehow it compares certainly to the strength of absorption of water vapor is much less strong. And in particular, it has a contribution at the level of 4.5 micron. So here is 1, 2, 3, 4. So it's run here. It's probably the difference between the blue model and the white model. Methane has, if it's there, some contribution in the near infrared and around 3.2 micron in the spectrum, and is probably the difference between this yellow and this blue. So again, the infrared is really dominated by water vapor, again, because we don't have, in general, so many extra information to trace down the other molecules. In the visible, that's where, on the contrary, we are dominated by scattering and potentially by hazes on some clouds. And here, there are some different models assuming different parameters for the cloud on the hazes model. So I was talking about CO, and in fact, CO was really detected, I should say, for the first time from the ground by Snellen and collaborator. Adam has already shown this observation more from a point of view of dynamics and showing that can potentially probe winds in the atmosphere. Here I'm showing you from a point of view of chemistry. And so the detection of CO from the ground is very useful because, as I said, from space, it tends to be, the signature tends to be washed out with the contribution of a stronger signal. So we know that it's there, and is there for some of the Jupiter that has been looked at. Certainly this technique is quite promising as a complementary technique with space, because from space we can look at typically some broader wavelength range that we can do from the ground, of course. But in the ground we can look at a narrow interval, spectral interval at very high resolution, and so the two information are very complementary. And as Adam also suggested, most probably this technique is probing a slightly different altitude with respect to where we're probing opacity from space. So having the two techniques working together is actually a big plus. So I show you some of the atmosphere for these hot Jupiters, and if we now move to colder and heavier objects like super-Earths, certainly one of the most studied super-Earth is this GJ1214b, and we're talking about 6 masses super-Earth, about 450 Kelvin. And of course, it's an extremely interesting object, and because of that, it has been looked at by many teams, and again with different instruments. Now, as you can see, compared to the spectrum of the hot Jupiter, well, certainly is a much more challenging type of observation. If you look at the level of precision that you need to have, this is a 10 to the minus 4 here, to really understand all the spectral features. This is much more challenging. Also, the star is relatively faint, so it's clearly not very easy. What we are taking out of this measurement is that overall the spectrum seems to be much flatter compared to many of the spectra that we are seeing for the hot Jupiter or from the Neptune. It could be suggestive of an atmosphere that is heavier than hydrogen as an overall statement. Some measurements in the near infrared with the WSC3 seems to be more suggestive of some clouds, but the two information are not necessarily, they could be both true in a certain sense. So bottom line, I don't think we can be really so conclusive yet about what is the real composition of this planet, and hopefully new generation of instrument might provide us with new information. This is actually a measurement that, sorry.
So, can you explain qualitatively why the precision of the creeper data is so much better than the precision of the Verta data and WSC3? What changed between the observations or production techniques?
Well, the new observations were taken, and so in Kreiber they were able to pile up more observations. And so due to the new observation, the paper suggests that the spectrum is much flatter, and so that's how it was interpreted as due to clouds. But again, it is true that WSC3 is just probing a relatively narrow part of the spectrum, and to understand whether it is really clouds that is creating this very flat sort of spectrum there, or there is a combination maybe of clouds or an atmosphere that is heavier, we need to look at the other measurements. Unfortunately, many of the other measurements are taken from the ground, which means it's quite challenging for this kind of planets, especially in the infrared. These are 2 Spitzer data. But as you can see, there's still a bit of scatter, and so it's not really obvious to conclude on this planet. Okay, so this is actually a new spectrum that was analyzed by Anglos Charas from my team at UCL, and is an AstroPH now. And what we looked at here is basically some measurement with the WSC3 around 55 Cancri, which is another very interesting super Earth. Here we're talking about a super Earth that is extremely hot, while GJ 1214 we were looking at 450 Kelvin, so towards the cold side of the kind of planets that we can probe today. 55 Cancri is extremely hot. We're talking about 2000 Kelvin or so, so the measurement that I'm showing you here are quite interesting, because this seems to suggest that actually, first of all, the spectrum is not flat. There is a modulation here, and the modulation is actually not so negligible for the type of planets that we're looking at. It's a super Earth, so the kind of gravity that you have is pretty high. So in order to explain this sort of bump, you actually need not only to have an atmosphere, but to push the atmosphere to be quite hydrogen rich, so relatively rich in light elements. So this is the relatively sure thing that you can say about the spectrum. If you want to try to interpret what's going on here, then of course you're going much more into the speculations, because you really have just one bump. The one bump is compatible with HCN, which is actually quite intriguing, because if it's true that this bump is HCN, and the fact that we don't see any signature water should have a strong signature up here, might be possibly suggestive of an atmosphere where the CO ratio is actually relatively high. But again, this we're going a bit more in the speculation. What to me is quite interesting is that this observation seems to suggest that there is an atmosphere around this planet, and also that it might be hydrogen rich. Yes?
If you have hydrogen, the light element around the planet is relatively small in
very close to the closest star, how can it keep that distinct?
Well, this is actually more a question that I would ask to David, because the kind of, I'm not showing this here, but it's on the paper in Astro PH. We did some simulation to see what kind of pressure was compatible with the signature. And it could be an atmosphere around 1 bar, slightly thinner, slightly thicker. So the question I have for David from formation and structure perspective, do you think that a super Earth with an envelope of hydrogen is something feasible or not?
I think it is, although I'm actually involved in a project with Jack Lissauer and Burkhard Millitzer and Leslie Rogers on the possibility that these atmospheres get replenished. That is, when you built the planet, it was actually hot enough and high enough pressure inside that you could actually put some hydrogen inside the planet. And then as the atmosphere goes away, it could actually be replenished by outgassing, even though it's primordial gas. It's not clear that works. And of course, it is a question of exactly what the temperature is, basically what GM upon C squared is relative to the radius of the planet, the sort of thing that Ruth talked about. But there is indeed an issue. There is a tendency for these bodies to lose atmosphere, and so you wonder why they still have it.
So, again, I think is an intriguing observation, and we shall see whether there will be new observation. For ACN, I'm afraid we need to wait for new generation of space instruments, because it is actually a relatively weak line of ACN. There are many more stronger lines at longer wavelengths, but we don't really have the spectral capabilities today to look at those.
Are you arguing that it's a hydrogen atmosphere because of the height of those vapors?
Yes. Yes, actually we were not believing ourselves too much that there was so much hydrogen, so we really tried to fit much heavier elements, but not just the inverse model, but even just brutally forcing things seems to be suggestive of an atmosphere that is relatively light.
What's the instrument?
WSC3. I realized that I haven't put the reference. It's Ciaras et al. And it's an Astro PH. So if you want to look at the detail, it's there. Okay, so we talked a bit about transient spectroscopy, but the other technique that has been used very successfully is eclipse spectroscopy. And here, basically, we are counting on the fact that at certain points the planet is going behind the star, and so we can measure the star alone and use this information basically to subtract out the contribution of the star when we're measuring the star and the planet together. And so the net effect is that we're getting a spectrum that is either emitted or reflected by the planet. Emitted or reflected depends on the wavelengths you're looking at, so depending if you're looking at absorption or scattering. And also here we're looking at tiny signals, again, like in transient spectroscopy, of the order of magnitude in 1 part in 10,000. So the big difference, in a sense, with transient spectroscopy is that with transient spectroscopy, what is really very important, first of all, is the relative size of the planet with respect to the star, and then, of course, also how extended is your atmosphere. When it comes to eclipse spectroscopy, what we're measuring, again, is a ratio between the radius on the planet and the star squared. So that factor is still important. But then what we're effectively measuring is basically a ratio between the flux that is coming from the planet and the flux that is coming from the star as a function of wavelength. And so, of course, these are not black body, but if we're looking, for instance, at planets that have a temperature of 1000 Kelvin, and if your star is about 6000 Kelvin, there is a part of the spectrum that is much more favorable for doing this observation, and this is when the emission from the planet is maximum, and on the contrary, the emission from the star is start to decrease. And so in some cases, transit spectroscopy is easier for some planets and some atmosphere. In some other cases, eclipse spectroscopy is the way to go. In a few cases, you can do both, and this is great because we can really probe very different properties of the atmospheres. You probably remember that 2 days ago we talked about the Schwarzschild equation or radiation transfer, and I think also Adam basically derived that equation. And so this is what we need to use here basically to quantify this part of the spectrum that is emitted or reflected by the planet. And if we are in the infrared, I already shown the spectrum of the Earth before. This is just to say that in the infrared, what we're trying to retrieve with eclipse spectroscopy is simultaneously the thermal gradient and also the concentration of the molecule. So clearly I have more complexity. So on one sense it's great that this technique gives me access to the vertical thermal profile of the atmosphere, but on the other side, clearly this information is entangled with the concentration of the molecule, and so not always I'm able to disentangle these two. So this is just a bit of a caveat. This is an example of emission spectroscopy that was done again for one of the two most famous planets, ST21945b. And I'm showing this particular one because again it's a collection of data coming from Spitzer, IRS, IRAC, MIPS, and also NICMOS from Hubble. Some of these points in Spitzer might moved around a bit, which means maybe the model is not completely updated, but again this is just to show the kind of information that we have today for a few planets. Even thinking that all the data points are correct, as you can see, the problem that we have straight away is that there are some regions of the spectrum that are not really covered by observation, and these are the regions that clearly are injecting higher level of degeneracy in the model. So in some cases we are able maybe to suggest what are the molecules that can explain this behavior, but certainly when it comes to combining together the thermal profile and the molecule, as you can see here, many models potentially can explain the data. So this is a bit of a caveat on the degeneracy and the way we can interpret these observations. Looking at eclipse spectroscopy in the visible, eclipse spectroscopy in the visible is very, very hard because basically then the radiation coming from the planet is competing with the star in the part where the star is actually radiating more photons, so it's a much more difficult observation. So even if here we have just two data points and two broadband, is a difficult observation, and so is still very important and very interesting. So this is a measurement that was done by Evans and collaborator for HD19753b using Hubble in the visible. And the interesting point is that for some of these planets, we seem to see observations suggesting that the albedo is quite low. And for this one, that we have at least two bands and not just one band, it's interesting to see that one data point seems to suggest an albedo close to 0, but the other one, on the contrary, goes up to 0.4. Again, suggesting that then if you integrate the two data points together, you have an interesting information. Again, I think this information in general is quite interesting when we want to try to understand if there are some opacities in this atmosphere, in particular clouds or condensates. One would expect that a very low albedo can be explained potentially by some cloud features or aerosol features that are very dark in the visible. So clearly this information can help us understanding what's going on. I'm not touching at all phase curve because Adam did a great job yesterday in reviewing all that and explaining what is the meaning of this phase curve and how they can be used to constrain the dynamics of this atmosphere. But I just want to mention the fact that today the very first phase curve spectroscopy measurement have been obtained for one planet. This is how Jupiter WASP 43b. So what you're looking at here basically are observations that are obtained at different points of the phase of the planet. And so again, this is extremely interesting both from a chemistry but also from a dynamics point of view because then potentially this helps us to disentangle the information from the opacity and from the dynamics, and so clearly having more observation on this particular one, it would be really, really extraordinary. Okay, I mentioned as a technique transit, but I think direct imaging now really needs to be mentioned because a new instrument like GPI and Sphere and Subaru, they're starting to provide really fabulous new spectra of exosolar planets at larger separation from the star. And I think this is a very complementary information because with transit, we're looking at planets that are located very close to the star. And if you're talking about Jupiters, it means that sometime in their history, they must have migrated there because they cannot really have formed there. So comparing from a chemical and dynamical perspective, planets which have migrated close to the star, or potentially were born there if they're not Jupiters, with potentially planets which on the contrary form a large distance is fantastic because then we can look at, for instance, what is the effect of stellar radiation on this planet, the effect of radiation, and so compare the chemistry for these different objects. I'm showing here just one particular object, but there are many new spectra that are coming out, and again, the comparison with the transiting siblings, I think will be really very valuable. One downside of spectra obtained with direct imaging is that you don't know the mass and the radius of the planet, you just know the spectrum. And this is a bit more a limitation when you want to retrieve the information out of the atmosphere because, of course, the least parameter you know about the planet, the higher potential is the level of degeneracy. For the mass, I think you can solve the problem because my understanding is that many of these planets can be, for many of these planets, the mass can be inferred with Gaia. But for the radius, of course, there is a problem, and so it's an extra level of degeneracy. So, what we have learned from a decade of spectroscopy.
With Gaia, we must observe the years of tens or hundreds of years.
Okay, I'm not an expert of what Gaia will be able or not be able to do, but the conversation was done among a couple of people that were working on both on Gaia and direct imaging, and they seem to suggest that for some of these planets, Gaia might follow up and give some constraint on the mass. I haven't really a strong opinion myself, so. But they can constrain the mass also with that, or not. Yeah, my point was just on the mass, on the radius, not on the other parameters. On the other parameters, yes, but. Okay, so I show you a few of the current observations, and this is all great because I should start by saying that going to 10 to the minus 4 the flux of the star with current instrument is really tough, and so the fact that there is a community that is able to do that, I think it's really very positive and a big plus. But there are some downsides, and in general you've noticed that we have to deal with low signal to noise resolution observations. All the methods have intrinsic degeneracies. I haven't mentioned the intrinsic degeneracies of the transit measurement, but the intrinsic degeneracy is that you don't know the radius at the 1 bar or 10 bar level if you're talking about a Jupiter, meaning to a degree you have some problems sometimes to renormalize the overall opacity. So how can you distinguish, for instance, a planet that have a smaller radius, but for instance much more water vapor pile up in the atmosphere, or on the contrary little water vapor but basically an overall opacity at the 1 bar or 10 bar level that is higher. So there is an intrinsic degeneracy with transit spectroscopy. I mentioned already the eclipse and the red imaging one. So they all have some pros and cons, and so ideally the more technique that we can find to probe this atmosphere, the better it is. Data are sparse, and we don't have enough wavelength coverage, so when we try to retrieve the information is difficult. When we have raw wavelength coverage, and I show you for a couple of examples that we can cover more or less the entire spectrum, although in a sparse way, the observations usually are not simultaneous, and again the danger there is that instrument might not behave the same way. The atmosphere might change. Of course, we know that brown dwarfs are showing variability, and so maybe also these objects, we expect that also these objects as planets might show some variability. I already mentioned the fact that absolute calibration, the level 10 to the minus 4, is not guaranteed today. And again, a caveat when we want to combine observation at different wavelengths taken in different time. I think the bottleneck today is the fact that instrument systematics are really difficult to disentangle from the signal. So we are more limited by the systematic than by the number of photons that we have. Yeah. So this is particularly true for this very weak signal. And then of course there is stellar activity that is potentially one of the largest sources of astrophysical noise. And if you're doing your observation relatively far away in the infrared, then to a degree you shouldn't be affected too much. But if you're pushing towards the visible or the UV, then you really need to worry about this potential source of noise, especially for transit spectroscopy. Eclipse to a degree is less affected. Okay, so what are the way forward? As I said, systematics are the bottleneck. So what can we do today with the data to improve? I think, first of all, the fact that despite all this, we're still getting a really very interesting result. It shows that there is a way forward. And then on top of that, I think we really need to learn from current instruments, because even if they are not perfect, it's a perfect training to understand how to deal with this difficulty. So we will be even more prepared for the future. So can we still do something with the data? Yes, actually there is an ongoing research activity on by many teams really to how to extract the signal in the best possible and also most objective way. And so I will talk about just a bit about the kind of the trending methods that are being used in the field, and we'll focus in particular in unsupervised machine learning. But again, I could talk for hours about this, so I will just give you some information about all this, because I think it's important. It seems to really start to make a huge difference in the way we can learn about this atmosphere. And by the way, all these techniques were sort of invented either by cosmologists or some other neuroscientists, sort of some other branches of science. And so I think trying to see, because they have very similar sort of problem, and so applied to exosolar planets seems to sometimes to work well and to give us some hints. One is principal component analysis, and you probably know this technique. already, but basically the idea here is that you want to measure the highest variance, and so what you're trying to do is to use an orthogonal transformation and use a basis that basically separate your observation in principal component, and then if your observation is sensitive to this, then you might be able to separate basically the signal from the systematic. Principal component analysis have been applied successfully, especially in the right imaging. It seems to work very well. And then many teams have been using this now for transit in exosolar planets. What is the problem with PCA? Well, the problem with PCA is that you're assuming basically some a Gaussian sort of signal, and so when you have a non-Gaussian signal, or when from some reason your geometry is not good, basically, and trying to, for instance, for orthonormal basis in this particular case is not really the right way forward, then PCA basically fails. But there are other techniques that are being used, like independent component analysis. Here, basically, what you're trying to do is to separate. You have the observation that, of course, are a mix of the signal from the planet, the astrophysical noise, the systematic, and clearly when you observe that, you don't know how to separate all these sources. So ideally what you want to have is to find basically a way for which a linear transformation that give you S, so basically a series of vectors where each vector is representing each of the sources, so the signal from the planet, the systematic from the instrument, the astrophysical noise. And of course, this is easier to be said than to do, but actually trying to optimize the statistical independence of the source seems to work pretty well for some of the instruments. What does it mean, optimizing this statistical independence? Well, a couple of things about Shannon entropy. I'm sure you have seen Shannon entropy before. Shannon entropy is a way to quantify the information content, for instance, of a particular vector. And basically, if you calculate the Shannon entropy for a Gaussian distribution of points, this is typically the maximum entropy for a similar sort of distribution with the same variance and the same mean. So if your signal now is compared to another signal that is Gaussian, your signal is typically non-Gaussian, and if you compare it with a Gaussian signal with the same variance and the same mean, you can basically calculate what is the distance between the two Shannon entropy, which is called negentropy. And since you really want to maximize the non-Gaussianity of your component, and the reason for that is that you really want to keep each of the component with the maximum information content. By minimizing the negentropy, that's how you can basically divide the sources. Now, this seems to be quite theoretical, but actually it works pretty well on some of the space instruments and also ground-based instruments that have been applied to. In particular, on Spitzer IRAC, Giuseppe Morello is a student in my team at UCL, and he has used ICA basically to try in particular to look at a relatively controversial measurement with Spitzer, where many teams were finding different solutions. The reason why usually many teams find different solutions is that because you're dominated by systematics, you need to have some hypothesis about what your instrument systematic looks like and then correct for that. And in many cases, the disagreement is how to basically describe your instrument systematic and then correct for it. In many cases, people agree. In other cases, they don't. Maybe one is using a second-order polynomial, the other one a third, and all of a sudden the result doesn't agree and there is a debate. And so we try to use ICA as a way to be more objective and not injecting our own prior on the instrument. And for many of these planets actually was a very good solution, because we could find quite consistent series observation. For instance, what you're looking at here is a series observation that were analyzed for the Spitzer-Irlak Challenge 2015. There was a challenge this summer where basically many teams using Spitzer were invited to participate. And as you can see here, ICA is performing well, and Wong et al. Is using our different technique, but also finding very consistent results. And so the fact that today many teams are really working hard to try to use more objective statistical technique is certainly a plus for the field, because it means that the disagreement hopefully will be less in the future. ICA has also been used for instruments like NIGMUS, and as you can see, you can trend well the signal. This is the transit line curve from basically the instrument systematic without necessarily injecting this information before. It has been used also for Spitzer IRS. In this particular case, you need to use it in combination with our technique, but again, it's very useful. For the WSC3, well, WSC3 has its own systematic, like any instrument, and it turns out that since the detector are very sensitive, and so just staring at a planet, potentially you can reach saturation very easily. So people have been proposed a different way to do observation, which is basically scanning mode. So basically Hubble is doing sort of movement in order to collect less photons. And so this has been really used for the past months and couple of years in a very effective way. Well, basically, you're distributing the photons on the detector in a better way, and you're exposing your instrument in a small amount of time, so you're becoming much more efficient. But because you're doing this, of course, there are some systematic that are coming out. And so, for instance, we have been developing a sort of simulator to look at all the single potential systematic, and so use the simulator basically to see how this correlation, if there is a correlation between the systematic or not. So this is all to say that there is a lot of work in the background that is going on really to address the point of the fact that these observations are very difficult and they need to be really carefully looked at. Okay, in the last part of my talk, I think I've probably bored you to death with instrument systematics, but I want to talk a bit about spectral retrieval. And so we have seen together in the first lecture a bit of spectroscopy, so basically what a spectrum is and why a spectrum is as it is. But here I would like to focus a bit more, given an observed spectrum, how can we interpret it? And I mentioned already there are several degeneracies in this spectra. And so how can we quantify the degeneracy and come up basically not just with a solution, but a solution also with the level of confidence that the solution is not completely crazy. And so many teams have started to work at inverse technique for spectroscopy, sort of spectral retrieval. And also there is a collective effort in producing some common paper to sort of compare these models and see whether there are any differences. And again, I think for the field this is really very good, because it reduces potentially the differences and the debates. I'm describing you a bit the retrieval that we have at UCL, but again, as I said, there are other retrieval around with some differences or some similarities. Certainly, most of the retrieval today are fully Bayesian sort of retrieval, and so they clearly can probe the parameter space of the solution. Solution mean what are the molecules present in the spectrum, and not only what are the concentration as a function of altitude, but also what is the thermal profile. And all this probing the parameter space is done in a fully Bayesian way. Again, this is common with our retrieval. On our side, we have a bit the help of the opacity line lists that are produced in our university, and so somehow we can speed up a bit the part on calculating the cross section because of that. Certainly, a part that deserves a bit of a discussion and thoughts is the prior. As you can imagine, if you're looking at a spectrum that should tell you about a planet that you don't know what it's made of, you don't know anything about to start with, you can't really start by assuming some very strong priors, because if you do that, you're basically sort of forcing your solution to go in one direction. And this is perfectly fine if you're looking at a planet in the solar system or the Earth, because you know so well already where the solution more or less should fall into, that you can sort of use some gradient-based method to get to the more precise solution, knowing more or less where you want to go. But for an exosolar planet, this is very, very hard. And so the question is, how can you quantify the prior? Some models are using basically some assumption about what the TP profile or the molecule should be. But again, the risk a bit is that you can inject some bias in the solution. What we have tried to use is actually what we call the Marple model, and it's basically a sort of facial recognition sort of algorithm that's using PCA. So when we have an observed spectrum, of course we never observe a spectrum as beautiful as this one, but the point is, if we have an observation, then we can use basically this module as to constrain the prior, so not to get to the solution, but to constrain the prior. And so if we start, for instance, by saying the number of molecules possible are 20 or 30, which clearly is impossible to look at the parameter space of all these species together. But if we're looking at what are the most probable one present in the spectrum, and this is what this model in particular is doing, then you can constrain a bit the parameter space to start with, and then do the full retrieval with the Bayesian method and be, on the contrary, be very, very precise. So what you usually get out of these retrieval models are basically some distributions. These are basically all the potential molecules that are present in the planetary atmosphere, and what you're looking at here are some distribution with the mean that is the most probable concentration of that particular molecule. And here, for instance, you have the temperature profile, and you can have other parameters. And then the idea is that you look at the correlation among all these parameters. So this kind of models do not only tell you more or less what can be the solution, but also the level of confidence with which you should treat the solution, and also whether there is some strong correlation between parameters that are basically telling you that you can't really get to the absolute value of particular species or temperature with that level of precisions. So this again is revealing very, very useful to understand better the not just the observations, but also the interpretation of the observations. Yes, please.
The global spectrum is supposed to be a linear combination of spectrum of individual molecules.
Yes, correct. So basically what the direct model does is, so what happens is you constrain the number of species that you want to look at, molecular species. You constrain more or less the temperature environment. And then basically you use some Bayesian method, typically MCMC, or in this case multi-nest. and you basically look at you scan, brute force the parameter space, meaning you go through all the parameters, you produce the red model, and then you compare the red model with the observation, and you calculate the likelihood, which I think it's here. It was here, yes, the likelihood, yeah. And then what you can do with multi-nest is actually not just calculate the likelihood, but actually integrate over all the likelihood for all the parameter space, which then tells you the confidence level at which you can assume this molecule is there with that concentration and so on and so forth.
Do you use the maximum likelihood or the expectancy?
Well, for this, again, it depends a bit on the method that you're using, but for this one, we're using this likelihood. But then you have sort of the integral over all the parameters of the likelihood here. So for multi-nest, you're calculating the real likelihood, the real value. Okay, so I will not spend too much time on this because, again, it would be really too long. But since, quite rightly, you mentioned linear combination of components, actually, sometimes things are non-linear. And to address the problem of non-linearity, we looked into deep neural network, which basically are new statistical techniques that are using multiple levels of ICA to get to the non-linear part. And again, I don't want to spend too much time on this, but this is just to flag that also the question of linearity has been looked into. Okay, yesterday somebody asked how many molecules we know with a relatively good precision today, and so this is the table. These are the molecules that are already available and quite useful, and these are the ones that we would like to see done shortly. Maybe there is already some information about this molecule, but for some reason is not optimal, at least is not optimal for all the wavelengths. Okay, the remaining of my time, I just, yeah. Well, this is a table that is put together by spectroscopists, so presumably what they mean is probably that it's bad. For instance, it could be bad because they have the information at room temperature, but not a high temperature, for instance. So red means that some information is incomplete. I would bet that this, certainly I haven't seen any line list for oxygen at very high temperatures, so that is certainly a problem. I don't know whether on top of that there is something more, but clearly for the atmosphere we're looking at, high temperature is quite important, as we discussed a couple of days ago. So in the 10 minutes that I have, I just wanted to say something about the future. The future is certainly very bright, in particular for finding new planets, because I'm sure that in the past days you've already heard that many projects from space and from the ground that will happen in the next decade, and so I think we'll be very fortunate. We will have several very interesting planets to look at. But if you're more interested in spectroscopy, what will happen after Hubble or Spitzer, what we're using today? Well, certainly JWST, ELT, and the TMT are the new generation from the ground and from space, and being larger and covering even broader wavelength range, that will be certainly much better than what we're using today. And so I'm sure all this telescope will provide a very good contribution in the understanding of this extrasolar atmosphere. I will tell you about two space projects that I'm involved on, Ariel and Twinkle, that ideally are space mission that we would like to see launched to provide basically a dedicated mission, and so the multiple spectra for many planets in the future. So just a few words about these two projects that I'm afraid are not yet in the launch pad. But anyway, Ariel is one of the 3 competitors for the ESA M4 mission candidate for launch 2026, actually, not 25. We're talking about a mission concept that sees a 1-meter class telescope in L2. So being L2, it means very stable and high visibility of the sky, and the stability is fundamental for doing transit spectroscopy. And the spectral range should be between 0.5 in the visible and 8 micron in the infrared. And the ambition is to look at 500 exoplanet atmospheres. And so the focus on Ariel will be on hot planets, and we can select from super Earths, even Earths in some cases, if they're hot enough around a very bright star. Neptune and giants. And the reason why hot planets are a good option is because they can be a natural laboratory for chemistry and formation study, because we think the atmosphere should be more the window in the planetary bulk composition to a degree. Of course, if many species are sequestered out of the atmosphere because the temperature is cold, it's much more difficult to probe them. But for very hot atmosphere, some of these chemical species are in a volatile form, and so they can potentially be probed through spectroscopy. And so the idea is to have then a catalog of spectra for all these species and potentially see whether we can really think about a nature diagram for planets like Tristan was talking about today, or whether on the contrary all these planets seems to suggest they have really a unique sort of characteristic. The other, yeah, please.
Stability over a few hours, which would be enough for getting trends that are secondary measurements, but not enough for a phase curve. Or are you not planning to do phase curves?
We do plan to do phase curves. I think there are 2 requirements at the ESA level. Is usually a very strict requirement, meaning if you don't meet that requirement, the mission is a failure, and the goal, which means you want to do that, but to a degree you're not compromising entirely the mission if you're not really able to do that. So the strict requirement is over 10 hours to make sure that you can really do on that baseline very well transit and eclipses. The idea, of course, is to extend that to multiple hours. And in any case, you can also think of doing the phase curve by sort of patches that you sort of put together. So certainly asking a stability of a few days for a space missions, no engineer will ever tell you that you're asking something sensible. So of course, as a scientist, one can try, but certainly 10 hours seems to be really feasible. And then of course the goal is to be even for longer duration. But yes, the plan is to do many phase curves. Okay, so the other mission concepts that we're working on is a much smaller mission concept. We're talking about Twinkle. Twinkle is actually, a concept for an off-the-shelf sort of platform coming out of SSTL platform that
when you listed the things that you would have wanted to have, you could have just written echo mission.
Yeah, just you mentioned the eclipse spectroscopy. So basically, you subtract the spectrum of the star alone with the from the spectrum with the transit. But would it be valuable to see to try to adjust the spectrum on the whole orbit? So. Or is it the phase spectroscopy? Yes. Yeah, okay. Okay. Alright. Okay. I was not sure. Okay, thanks. And does it improve much the result, or?
As far as the wavelength information. Thank you. The day side's pretty good as far as the wavelength information, but I think it's sort of a bit on the hairy edge for the night side. I showed the white light curve from here. This is the one that was like just plummeted to almost zero flux on the night side. That was kind of an outlier in that trend that I showed. So that's quite clear in the white light curves. But when you start subdividing it into numerous bins, the error bars go up. And then, even though in principle it's like an awesome method, I think in practice getting with the wavelength information out, like if you look here, the error bars are kind of comparable to the size of some of the features, and there's a bit of scatter, which is not clear is actually real. So, but you know, with better signal to noise and so on, this is a really promising technique.
Thanks.
Yeah, you briefly mentioned deep neural networks and machine learning. So how is it going to look like in the future? Is it just like astronomers just using it as a black box, or do you think there will be some kind? Is it necessary to actually start like more concrete collaborations with people working in machine in artificial intelligence and that stuff?
This might be jumping the gun a bit, but would it be much more of an obstacle to probe an exomoon atmosphere?
Today, I don't think.
Well, yeah. Yeah.
you're thinking about the sort of a transitor eclipse around the giant planet, and so you're talking about, again, depends on being the moon, which was the argument possibly, but I would guess it's a very tiny signal, so it really seems unlikely. Certainly absolutely unlikely today, whether it can be done with the generation, it still seems quite challenging to measure.
Speaking about exomoons, imagine, well, if one would imagine that there's a very large exomoon with large atmosphere in it, how would it be possible to disentangle which molecules, or while observing which molecules or spectral features belong to the planet and which to some satellite? But what I mean is taking a moon like with huge atmosphere, like I don't know, Titans and something like that, which would be extended. I don't know how much, but so basically it didn't do any effect.
You said you can't derive the radius via direct imaging, but why wouldn't you, when you have like the luminosity, maybe even spectral information from new direct images, so you can get the absolute luminosity of the planet, and when you have the distance, you can simply calculate its radius or not?
Yeah, I just wanted basically to say something like that. So there's this planet, I think it's 51 Peg-B, if I'm not mistaken, and they have done what you suggested, but they fitted the radius and the effective temperature and everything using a cloudless model and using a model with clouds, and they weren't sure which one was better to use. One gave them a radius of 0.7 Jupiter radii, and the other one gave them a radius of 1.1 Jupiter radii. So, I mean, like there's so much uncertainty in the model, you get really different results. Yeah, I mean that's just one thing you can play around with. Sorry, yeah, right, that's what I meant, sorry. Yes.
Any more questions? Let's thank Giovanna again.